Welcome to the slop farm. Enjoy the video.
You start by defining the theory and conventions you will use. State the Lagrangian, label coupling constants, and pick dimensional regularization with epsilon equals 4 minus d and scale mu. Next, derive Feynman rules so you know which vertices and propagators contribute. Then identify the one-particle irreducible green functions that need renormalization. These determine which counterterms to compute. Once done, set up loop integrals for the lowest non-trivial order. That's the first actionable computation step. Now compute the loop diagrams and focus on extracting divergences. Perform integrals, expand in epsilon, and collect 1/epsilon poles. Those coefficients are the key data. Use minimal subtraction or MS-bar to define z-factors that cancel the poles. Write bare coupling G0 as mu epsilon zg, g epsilon g. Once you have zg to the computed order, differentiate with respect to mu keeping bare quantities fixed. That differentiation links the pole structure to the beta function, coefficients explicitly. Finally, obtain the beta function by differentiating the renormalized coupling at fixed bare coupling. Beta g equals mu dg slash d mu g0. Use the relation g0 equals mu epsilon zgg to convert zg poles into beta coefficients, giving the perturbative series such as beta equals minus epsilon g plus beta 1g3 plus beta 2g5. Make sure to simplify and express coefficients in your chosen normalization. If results look wrong, recheck symmetry factors, diagram combinatorics, and regularization steps. A missing factor of 2 or sign is the common culprit.
Thanks for watching. Consider subscribing if we helped you today.